Okay, good afternoon, everyone. I am Sophie, and I am a machine learning scientist at ASOS.com. I am originally from Belgium, and I did a PhD around using fine-grained behavioral data. And now I'm working in the recommendations team at ASOS. So today I will talk about how we try to personalize product recommendations at ASOS. So I will try to give an overview of the past year in our recommendations team and the journey we plan to start and how it turned out. I'll start by quickly giving an introduction to ASOS, but I guess most of you will already be familiar with ASOS. Secondly, I'll demonstrate the maturity of our recommendation system, and then I will talk in a bit more detail about the recent transformation our team has undergone, together with showcasing a project that resulted from this new team structure and from this new way of working. So most of you will probably know, but ASOS.com is a global fashion e-commerce company that offers clothing and beauty products to 20-somethings. We have a large number of brands on the website, and the most important brand for which our customers come back is our ASOS design brands that are created in-house. We have around 20 million active customers, and at every given moment, we have around 90,000 products online. Approximately 5,000 products are added on the website each week. And as you can imagine, given the rate at which we increase our product catalog each week, our recommendation is very important and central to the customer experience. So given the importance of recommendations on our website, the recommendation systems engine at ASOS is the most mature product we have in our AI team. We have implemented a matrix factorization variant to provide our customers with relevant product suggestions. And next, I'll show you how we use the resulting customer and product embeddings from that matrix factorization on our website to help customers navigate the product catalog. So here you can see your edit. This is a carousel that is shown on the homepage, and it shows personalized recommendations to each customer based on that customer's previous product views, previous purchases, and save for later actions. Next, we have the brand recommendations, where we aggregate the product embeddings to a brand level, and in this way recommend specific brands to the customer, which can be very valuable given that we have so many brands on site. One of our other products is the Buy the Look carousel. So when you click on a product and you visit the product page, which you can see here on the top left, we call this the hero product. When you scroll down, you will get this carousel, which will show you outfit suggestions that go together with the hero product. And next, we have the You Might Also Like carousel on the product page as well, where the customer sees suggestions for other similar products that are available on the website. So this video here is one of the testimonies that our customers really love what we recommend to them in the You Might Also Like carousel. And this really helps our team to show the business that there is value in iterating on and keep on improving these recommender products. And you can see the video with the link below. So up to now, I've shown you some of the applications of our recommender system engine throughout the ASOS website. And what I would like to focus on now is the recent transformation that we went through within the recommendations team and the major impact that it has had on dynamics of the projects that we do inside this team. So here you can see an outline of the structure of our team, the way it was before the transformation. So on the left, you can see 4 machine learning scientists all working on their own project and doing the research on that project. So one scientist would be working on an outfit recommender, another scientist would be working on size recommendations, another one would be researching and working on homepage personalization, etc. So very different projects. And then these projects were quite research focused. So for example, take a scientist that is working on a size recommendation project. So the scientist would do some initial data analysis to see if there is value in the project, and then to get a feel of the data as well. Then he would go through the relevant literature, build a baseline model, and then iterate on that model with the goal of building a complex machine learning model that would perform very well on some offline evaluation metrics. So the research for this would vary between projects, where some projects could take up quite a few months. And as you can see, not all projects would make it into production. And the reason that some projects wouldn't make it into production was because that the next step would then be to prioritize a project within our platform and assign engineers to it. And these engineers then had to get up to speed to the project and then productionize the model together with the machine learning scientist. Eventually, when everything was ready, the model would be tested with an A/B test, and after a few weeks, the scientist would get a view on the online performance of his work. So there are some clear and major disadvantages with this way of working. First of all, it took quite some time to get something into production. This is because the scientist would set out to build the best and the most complex model on the one hand, and then on the other hand, you would also have this handover to the engineering team that would also take up some time. Secondly, the scientist wouldn't also be sure whether his or her model would be put into production. This would be dependent on business priorities at that moment, which had an impact on the availability of engineers. And then another major disadvantage that our new way of working is hoping to address is the fact that the scientist would iterate on his model based on the offline measures that he or she has defined in the beginning, but you wouldn't know how well your model would have performed in an online test only after a few months. So it could be that this very complex neural network would only have a very small improvement compared to a baseline model, but you would only know this after a couple of months. So we tried to address this with this new kind of setup for our team. So the major difference would be that we wouldn't work in silos anymore. We would have 2 or 3 machine learning scientists that will work on one project together. We have seen that this improves the collaboration between our scientists, and it increases the speed with which projects can be put into production. A second change that we made was that we brought the machine learning scientists and engineers in a tighter knit team where the productionization would happen in parallel to the research. And this removed this handover that we had, and it also reduced the time to put a project into production. And the most important change that we introduced was to work in shorter iterative cycles. So instead of our scientists working on implementing, for example, a complex recurrent neural network, we would start with a very simple baseline model, which I will give an example of later on. And then we would test this as soon as possible to get feedback from the online test, which would then guide us through our future research cycle. So when following this approach, while the test is running, this downtime allows the scientists to work on another iterative improvement of the model and have that ready to be tested when the other test ends. So this majorly increases the number of tests that can be run and the amount of learning that we can do as a team. It also allows us to make our models more complex in an iterative manner, and it allows us to have more of a view of what changes to the model have what kind of impact on the online metrics. So this new way of working, and with our tightly knit team of engineers and scientists, we decided to improve on our You Might Also Like carousel, which is a product that has the most click-through rate on our website. And as mentioned previously, this carousel is shown when you scroll down on the product page, and you can see recommendations for similar products. And also, as a reminder, our recommender system is based on matrix factorization, so we have embeddings for all our products and all our customers. So the main goal that we set out when we started this project was to improve product recommendations by enriching them with some kind of personalization. So currently, this product carousel is based on the hero product that the customer is looking at, and it takes that product vector. It then takes the dot product of that hero product with all other products in our catalog, and it shows the 16 products that have the highest dot product with that hero product. So there are a few ways that we initially thought of on how we might personalize this. And the first thing that comes into mind is to take into account the customer that is looking at the hero product. In that way, 2 different customers looking at the same hero product would see different recommendations tailored to their specific tastes. This improvement would also be quite easy because we already have customer vectors, so it wouldn't be that much of an effort. And more importantly, it would be a very good first baseline model to build and to quickly put out there to test and to get some feedback on. A second way that we thought of personalizing this would to not only look at the customer that is viewing the product, but also take into account the customer's intent when he is looking at that product. So what is the customer looking for when he is browsing on the website? So maybe a customer is shopping for a party dress instead of a more casual dress. And if we take into account that information that is present in the customer's session, we might improve the relevance of our recommendations even more. So we started out by doing some initial analysis that would demonstrate that there is value in personalizing these recommendations. And more specifically, we wanted to answer the question, does a user have a focus in a session that can be inputted into our model to help us recommend more tailored products? So here you can see just a very high level example of a session of a user on our website. And you can see that the user clicks on different types of off-shoulder tops. And then you can see that the final purchase is kind of a blend of the items that he previously clicked on. So this, together with some deeper analysis that we did, made us believe that there is value in building a session-based variant of our You Might Also Like product. But instead of immediately building a complex recurrent neural network with an attention mechanism, for example, which is what we would aim to build, we followed this advice from Andrei Karpathy, which is also in line with our new way of iterative building and testing. So we started out by ignoring sessions for now, and we just focused on taking into account the customer vector. We already have these customer vectors, so the research phase would mostly consist of building a training and a test set, finding out which offline metric to use, finding a way to combine these two vectors in a good way, and then look at the offline performance. And in the meantime, because this is not really a high engineering effort piece of work, our engineers could focus on building the capability of accessing session data in real time, which would then be available for us as scientists to do our next iteration on. And in that way, we could work in parallel. So here you can see I'll show the setup of our very first personalized You Might Also Like iteration. So we start by taking the hero product, which is the viewed item that the customer is looking at, and we will get the matrix factorization embedding for that product. Next, we have our user history, and the embedding that matrix factorization learns for our customers takes into account the previous view history, purchase history, and save for later history that our customer has performed on the website. Then, before we combine these two embeddings, we need to do some scaling because generally our item vectors take on larger values. And if we wouldn't do any scaling, this would result in the item vector always overpowering the customer vector. And then we would combine both of these embeddings with a weight, and then we would get a personalized embedding. So this embedding would then be inputted into a dot product with all other products in our catalog, and then we show the 16 highest ranking products in our carousel. So the main research question really here is what weight do we give to the item embedding, and what weight do we give to the customer embedding? So how do we combine these two embeddings? So this was the major research question that we worked on for our first baseline model. So how do we go about choosing a good weight for our model? So as an offline evaluation metric, we looked at the hit rate at 1 and at 16 because we show 16 products in our carousel. But here I will show the results for hit rate at 1. And so the hit rate is defined as how many customers purchase the first product that we recommend to them in the You Might Also Like carousel. So we go a step further than just looking at the click-through rate in this hit rate metric. So this plot here shows the personalized weight on the x-axis, which is the weight that we give to the customer vector. And on the y-axis, the hit rate is shown. You can also see a small dip in the orange solid line. This is because we had a failure in one of the AML experiments. So The dashed lines are the ones, the results that we got first. And this shows that for male customers, the best hit rate is around a personalized weight of 34%. And for female customers, this is around 32%. Given that a customer is visiting a specific product page, we would indeed assume that the higher weight would be given to the item embedding, as the customer vector captures information from further back in time. So the solid lines show the same plots, but here we only look at customers that have had no previous interaction with the purchased product. It makes sense to filter them out because they might add some noise. And in that way, we only look at customers that have bought a product because it was present in their You Might Also Like carousel and not because they were already planning on buying it. And this resulted in a small decrease of the amount of personalization to 26% for male customers and 28% for female customers. And so we assume that the previous browsing information might have been present in the customer vector, and that's why we were skewed towards higher weights in the dotted lines. So we settled on using 28% as a personalization weight in our first baseline model. So the next step was to start A/B testing this because the engineering effort was quite small. We had around 4 million customers in each of our groups, in our control group and our test group. And so here you can see the test results for the control group on the left and the treatment group on the right. So on the top, you can see the number of customers entering the test. And then on the second line, we can see that the click-through rate on the You Might Also Like carousel increases by 1.68%. So there is more interaction with the personalized recommendations that we offer. You can also see this higher interaction by looking at the third line, where you can see that there is an increase of customers putting products into their shopping bag. And then finally, the most important metric for us is on the final line, where you can see that there is an increase in conversion of 8.19%. So for us, the results of this test, which is just a very simple iteration of our model that is already in place, we really showed the value in investing more resources in personalizing the product recommendations at ASOS, and the value in doing these further iterations on the model and hopefully get something, a more complex model that results in an even bigger improvement, hopefully. So I hope that I was able to give you an overview of how we work and the type of the projects that we are working on inside the recommendations team at ASOS. We have started a subsequent iteration on this simple model, which I was hoping to present today as well, but everything got a bit slowed down by COVID. So hopefully I can let you know how that went at some point in the future. And in the meantime, if you have any questions, I would be happy to try and answer them. Thank you.